Thank you for giving me the opportunity. I am MST Nasima Begum, on behalf of my co-author shown in the slide, presenting the paper Optimizing Laser Micromachining Parameters for PMMA Microchannels, Experimental and Predictive Analysis of Depth, Width, and Heat Affected Zone. Microfluidic is a rapidly growing technology for application in biomedical engineering, chemical engineering. This microfluidic device passes liquid and gaseous substance through microchannel. The shape and dimension of this channel are crucial for effective fluid flow. Polymethyl methacrylate has been a popular choice compared to previously used silica-based substrates due to its affordability, ease of use, compatibility with human tissue, chemical stability, and dimensional quality. In creating microchannel, previously photolithography, chemical etching, and in some cases ultra-short pulse laser was used. However, the carbon dioxide laser micromachining is preferred for its speed, flexibility, and cost effectiveness. In laser machining, material thermomechanical properties mainly dictate the formation of channel shape and surface quality. PMMA is a good absorbent of far infrared and ultraviolet wavelength, so it is crucial to understand how machining parameters affect this heat-sensitive material. Previous researcher work on micromachining of PMMA focusing on different dimensions. The novelty of our work is we use finite element analysis and material temperature related properties to estimate the channel width, depth, and heat affected zone. The objectives of our research is to explore the impact of laser power, scanning speed, and the ratio on the width, depth, and heat affected zone, to predict channel dimensions and heat affected zone by coupling temperature dependent material properties and laser parameters to develop response models and perform optimization. The methodology is shown in this slide, where carbon dioxide CNC laser is used to create microchannel on PMMA workpiece, power varied from 20 to 80 watt, and scanning speed from 200 to 500 millimeter per second. According to design expert software, we get 11 experimental runs. Each of the PMMA workpiece having dimension of 40 by 20 by 3 was machined using single pass. The responses, channel depth, width, and heat affected zone was measured using optical microscope, and the amount of temperature generated on the work surface was estimated using COMSOL multiphysics software. Channel dimension and heat affected zone was predicted by coupling finite element analysis and temperature dependent properties. Response model was developed and optimized using response surface method. Then the result was analyzed, discussed, and some conclusion was drawn. Laser machining schematic diagram is shown in figure 1, where laser from the source is directed to 3 mirror and focus on the work surface. In FEA, the laser intensity at any location is defined by using equation 1. After defining block geometry, heat conduction was applied using equation 2. Initially, the surface was set to an ambient temperature of 20 degrees Celsius, and it is assumed that there is no heat loss. Cooling through convection and radiation was also introduced, and finally tetrahedral mesh element is added and simulation was run. Here are the results. During laser heating, temperature is adequate to vaporize PMMA. Since laser is a moving source, this temperature gradually decreased, leading to material removal up to sublimation point of 300 degrees Celsius. So beyond this point, base structure changes and resulting in the formation of heat affected zone. So we can see that in figure 3, this is the temperature profile towards the depth. So when materials start cooling until reach 300 degrees Celsius, we can get the material channel depth, and this is was calculated by cut point of temperature profile and 300 degrees Celsius. Similarly, in the middle of the channel wood, temperature was highest and it gradually decreases towards the wood. And until 300 degrees Celsius, we get the channel width, And beyond this, until 110 degrees Celsius, we get the heat effective zone. This table shows the experimental data of depth, width, and heat effective zone, and also the predicted depth, width, and heat effective zone, along with the temperature. All the response parameter, depth, width, and heat effective zone increase with the increase of P by S ratio. Because of as P by S ratio increase, temperature increase, shown in figure 3b. The response model was developed, shown in this slide. Depth, width, and temperature shows quadratic relation, while the heat effective zone shows linear relation. Then optimization was carried out in order to get a channel having depth of 105 micrometer and width of 300 micrometer with the aim of having minimum heat effective zone within the range of power and speed. The optimization was carried out under numerical optimization of RSM software. The optimal result is shown in table 5. Based on the highest desirability, 85%, the power approximately 47 watt and 500 millimeter per second speed give our desired width and depth channel with minimum heat effective zone 104 micrometer. The conformity experimental run was carried out at 47 watt and 500 millimeter per second speed. Results are shown in this figure. This is the depth, width, heat effective zone, and the COMSOL profile shows this is the temperature with respect to time. The result shows that the experimental results are closely matched with the optimization results. Individually, this is for the depth, this is for width, and this is heat effective zone. The COMSOL prediction was also closely matched with the optimal results. So, the experimental results and FEE analysis clearly show that as the power to speed ratio increases, depth of cut, width, and heat effective zone increases. The temperature is highest at the center of the beam, resulting in greater depth. Depth gradually decreases as the distance from the center increases. Heat effective zone form as heat is conducted across the channel surfaces below the glass transition temperature. The minimum heat effector zone, 104 micrometer, was achieved at 47 watt and 500 millimeter per second scanning speed, while getting 0.097 millimeter depth and 0.3 millimeter width. Finite element result and optimization result closely match the experimental run. Hence, the prediction can be used to analyze and make proper gesture. Thank you.